Okay, so you guys have been looking at gravitational acceleration, but then we also looked at a different way to look at potential energy. So we're going to look at a situation to show you how that works. Now, here's a spaceship above the Earth, and what's going to happen is, for whatever reason, the spaceship it's broken down, and the spaceship is going to fall down to the Earth. Okay, so what we're going to do is we're going to find out how fast is that ship going when it actually hits the Earth? So when it actually impacts speed, I guess, so to speak. So how fast is it going when it actually hits the Earth? And we are going to use energies for this. So if we start up here, at the very, very top here, this ship has potential energy. So it has gravitational potential energy, which is GMM over R. Okay, so we've done this calculation, or we've done this expression before, so we can use this to find out how much potential energy the ship has in, so I'll call it position 1, radius 1, where it starts. Now the radius for this will be from the core of the Earth, so that'll be the radius of the Earth plus the 12,000, and we can use that in order to figure out how much potential energy it has. Okay, so if we do that calculation, we can find out the initial potential energy of the ship. So putting that all together, we are going to have about 2.803 times 10 to the 11 joules of potential energy up there. Okay, and now what's going to happen is the ship is going to fall down. Now, as the ship falls down, its potential energy actually gets bigger because the radius gets smaller. So we are going to find out the potential energy down here. So let's find our second potential energy, which is GMM over R, and this time it'll just be the radius of the Earth because it's just sitting on the surface of the planet. And the potential energy will have gotten smaller. Or not smaller, the potential energy will have gotten bigger because the radius has gotten smaller. So having, if we put those numbers in, GMM, those haven't changed, the radius of the Earth in there. Now our potential energy should be higher. It didn't go a huge distance compared to the size of the planet, so it'll go up a little bit. Looks like we have 2.8086 times 10 to the 11 joules. So we went from 2.8033 up to 2.8086, so it got bigger. Now, we talked about this before, it's not about how much energy you have, it's about how much your energy changes. The change in energy is super, super important in this. So we don't really care about how much potential we have here, we don't really care about the potential there. What we want to know is what is the change in potential energy. So all we have to do is take those two and then we can subtract them and we can get the change potential energy. Okay, so if we subtract those two, we will get a change of potential energy of about 5.3 times 10 to the 8 joules. Now, not only is this the change of potential, this is also going to be the change in kinetic energy. So it had no kinetic energy up here, and it gained it as it went down. And the change of potential is going to be equal to the change in kinetic. So since I know that is the change in kinetic energy, I know that this is going to be equal to the 1/2 mv squared, and I can solve for how fast the ship is going when it hits the surface. So just your basic classic kinetic energy expression. So we'll take that change in energy, we can times it by 2. We'll divide it by the mass, and make sure you divide by the mass of the actual ship itself, because that's the thing with kinetic energy. And also don't forget to square root it, and we can find out how fast it's going when it hits, which is about 490 meters per second, and that's how fast it's going to go when it hits. And if you try and use the other, mgh equals 1/2 mv squared, it's not going to work very well. You might get close-ish for this one, but it's not going to work out very well. Now, the other part that kicks in is not only is this the change of potential energy equal to the change of kinetic energy, it's also equal to something else. Because what often connected potential energy and kinetic energy in the classical stuff that you guys did? Well, good old-fashioned work. So not only is this the change of potential is equal to change of kinetic, this is also the work that was done to bring the ship down. So again, it's all about how much, it's not about how much you have, it's about how much the energy changes. So there was 5.3 times 10 to the 8 joules of work that was done. And one of the great things that you can find out from work is force. So we could actually calculate how much force was actually used to bring the ship down. Now, one of the biggest mistakes people make in a question like this, if it asks for the force, is they'll try and use the GMM over R squared to calculate the force of gravity. No, that is not going to work out very well, because the force of gravity changes so much from one position to the other position, especially with the inverse square law. It works a lot better to use energies. Now, the only thing, of course, is when you use work equals FD, this will give you the average force, which is perfectly fine, no big deal. So if we do that, the work would be the 5.3 times 10 to the 8, and we'll divide it by the distance that it traveled. And the distance it traveled is the 12,000. So if we take that 5.3 to the power of 8, which is the change in energy, the work done, all that kind of stuff, and we divide that by the 12,000, we will get a force of approximately 4.4 times 10 to the 4 newtons. And again, this is the average force that was used from up here down here. And if you try and do the GMM over R squared here and here, you won't. It's not going to work. It's just, it can be done, but it's disgusting. It's a lot easier to do it this way. And some people that do, well, it's the average force. Well, just find the force here and double it. No, it doesn't work that way, because since it changes with an inverse square law, it doesn't just double or get half as big or anything. It doesn't quite work. It's a lot easier just to calculate it like this. It just works an awful lot better. So this is where the energies really kick in for things falling or going up or down from a planet or something like that. Now, this is where an important distinction kicks in between this as well as the other stuff you guys were doing with forces and FC. One of the biggest clues for what type of strategy to do is look at the radius. Almost spelled it wrong. The good old radius. The one thing about this energy thing is when the energies, this thing is going up and down, the radius is changing. When you guys were using forces and FC, it was an orbit, and that's where you use your forces of gravity and that type of stuff. So if it is a constant radius, like an orbit, almost guaranteed you want to be calculating forces, like GMM over R squared, mv squared over r. If it's a constant radius, almost guaranteed you're just going to calculate forces. If the radius changes, almost guaranteed you want to be using good old-fashioned energies, potential energies, kinetic energies, that type of stuff. So constant radius is probably GM over r squared equals mv squared over r, orbit type stuff. But if that radius is changing, even if it asks you for force, don't get suckered into using mv squared over r or GMM over r squared. If the radius is changing and asks for force, almost guaranteed you need to be using energy for that. It's a lot easier, it's a lot more efficient, it just works so much better. Okay, so let's look at another question, another situation, and get some more practice with this. Okay, so let's try this. Here we have a 180 kilogram astronaut with a little jetpack on, and he's 160 kilometers away from the surface of the moon, and he's at rest. And he's got like a little magic like jetpack that's going to give him like this little instant speed boost of 840 meters per second, which is only going to last for an instant in time, and we're not going to worry about the acceleration killing him or anything like that. So just nice little idealized situation. And what we're going to do is we are going to find out how far he actually goes. So how far will he actually be able to go before the moon's gravity actually stops him and maybe tries to pull him back? So maybe we'll also try and find the force to actually slow and stop him. We'll see how much force is actually used as well. All right, so since the radius is changing, this is about energies. Even though up there asks for force, we're going to use energies for this and sort of piece things together. Now let's just start by finding some energies. So over here, he has potential energy. So I'm going to find the potential energy of my astronaut at the beginning. So if I calculate his potential energy, that's GMM over R, and the radius would be the radius of the moon plus the 160 kilometers, so 160,000 meters, and that will be his initial potential energy. I got to calculate his first potential energy that he starts with. Okay, so I put those in there. I'm going to get about 4.644 times 10 to the 8 joules. So that's how much potential energy he has at the beginning. All right, now he takes off with 840. Well, I've got a V. If I've got his V, I can find the kinetic energy from that. So the kinetic energy that he takes off with, 1/2 mv squared. Now you do the 1/2, got his mass. I'll take the V and I'll square it. Don't forget to square the 840. I can calculate, we're looking around 6.33 times 10 to the 7 joules of kinetic energy. Okay, so I know he starts off with this much potential energy and this much kinetic energy, and as he goes further away, his kinetic energy is going to go down because he's going slower, and his potential energy is also going to go down because he's going farther away. I know the two changes are going to be equal. I know the change in kinetic and the change in potential are going to be equal to each other. So if he's going to go further away, his potential energy is going to get smaller by the same amount as kinetic energy does. So all I have to do to find his new potential energy out here, all I have to do is take that potential energy that he started with, that's this one right here, minus the kinetic energy, because the change in potential has to be equal to the change in kinetic. So my kinetic is going to change by 6.33, so my potential is going to change by 6.33, and the potential is going to get smaller. So if I subtract the two, I can get my new potential energy, and some rounding and stuff should end up with like 4.011 times 10 to the 8 joules. Now that I have his new potential energy, I can use that to find out his new radius. So that 4.011 times 10 to the 8 is going to be equal to GMM over, I'll call it radius number 2. All right, I've got my G, I've got my M, I've got my M, I've got my new potential energy. I can solve for my second radius. So my second radius will then be his radius at his new location way over there. So my new radius is about 2.2 times 10 to the 6 meters. Well, if I go back to the very beginning, the radius that we used out here, the first radius we used was the radius of the moon plus the 160,000. That first radius we actually used over here was about 1.9 times 10 to the 6. That's the value that you should have used in there. Well, if we've got the first radius was 1.9 to the 6, my new radius is 2.2 to the 6. All I have to do is subtract them, and I will know how far he went. So 2.2 take away 1.9, we're looking at 0.3 times 10 to the 6 meters, and that would be the distance that he traveled, or 300,000 meters. Okay, now if I want to find out how much force was used, well, that's no big deal. Force is equal to, and it'll be the average force, is going to be equal to the work done divided by the distance traveled. The work done will be the change in potential as well as the change in kinetic, which was this right here. The distance traveled will be that distance right there, so we can divide the two, and we can calculate the force that was actually used. And if we divide those two out, we should get probably around 210 newtons in order to actually slow and stop our astronaut. Okay, so here's a nice little question with, again, the whole change in energy idea. It's actually very similar to the classical mechanics stuff you guys did. Change in potential can give you change in kinetic, can give you the work done. It's all the same ideas. Just the potential energy formula is a little bit more fancy schmancy, but it still works. You also got to keep in mind that as you get further away, the potential energy gets smaller instead of bigger, but just be careful. As long as you change in energies, it works out to all the same ideas.